Hello AP Calc BC students or Calc 2 students from the college level that might be tuning in. This video is going to talk about the fictitious topic number 814 that I've added to the AP Calc course and exam description over work. A note to all high school students and teachers that work is not a topic tested on the AP Calc BC exam, but it is a topic that many schools might cover if they have a second year BC course to really flesh out the course and give it a true Calc 2 experience. Those of you who are enrolled in a a college Calc 2 class, you know what we're talking about, because sometimes work can be a pretty challenging topic in that particular class. So what we're going to look at in this particular problem is we're going to take a look at this idea called Hooke's law, which is sort of associated, I guess, with the idea of stretching or compressing a spring. And this is attached to a very well-known mathematician, Robert Hooke. Those of you may not be aware, Robert Hooke has a very interesting role in basically the determination of who is credited for the discovery of calculus, as Robert Hooke was a mentor, so to speak, of Isaac Newton and gave Isaac Newton a little bit of harsh criticism on an early manuscript that he wrote prior to his discovery of calculus. And that harsh criticism sort of led Newton to be very reluctant to publish anything for a while. And that kind of gave a few other mathematicians a little bit of a heads up and allowed them to kind of develop before anything was truly published. But in any event, Robert Hooke was the individual that's associated with this idea called Hooke's law, where we have F is equal to Kx. F is simply the force required to compress or stretch a spring as long as it's within its elastic limits, and it is proportional to the distance x that the spring is being compressed or stretched from its original length. The K value is this very important idea called the spring constant. It varies depending on what kind of spring that you have. Let's say that you have a spring that you can find from disassembling, taking apart one of those retractable ink pens, right? Click, 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 click. Well, you could find that that little spring might look something like this. Yeah, it looks like that spring, doesn't it? Real tiny, very easy to manipulate with your finger and your thumb. It probably doesn't feel like it's requiring any extra work to compress it any farther. On the other hand, let's say that you go to the underside of a vehicle. Let's say a really, pretty powerful, robust vehicle like a truck, a heavy duty truck or a Jeep or something. And you might see that part of the suspension system is one of those springs that looks like that. Now that would be a much more difficult spring to stretch or compress because the fact that it's got a lot more thickness to it. And so the K value is going to be very dependent upon that situation. Now, if we take a look at our first example, suppose a force of 50 pounds compresses a spring 5 inches from its natural length of 20 inches. Oftentimes, when a student starts to read a question like this, they kind of read a little too much into it, and they think that the original length of the spring matters. It turns out that it really doesn't. All we are caring about is how far that spring is changing, being stretched or compressed from its static state. So the 5 inches is the important piece. So if the force is going to be 50 pounds and the distance x is going to be 5, you can see that we can very easily use Hooke's law and obtain what's called the spring constant. Okay, as I said in my last video, I want to make sure that we are aware that I am going to be using imperial units for quite a few of these examples. I will probably switch to some metric units. I definitely have some metric units in a lot of my materials for my students to do their practice, Newton meters, right, the joule. But we're going to work with feet and inches, or I'm sorry, pounds and inches in this particular problem. So once we have our spring constant of 10, we can now use it to find the work to compress the spring 5 inches. Now to make that happen, we're just going to integrate our Hooke's law, which is now 10x, kx. Now understand, this is basically acting like our force, right? That's what the force was equivalent to. Now, once this is sort of attached to the DX, I want everyone to realize that that's going to play the role of the distance, right? It's partly playing the role of the distance. It's kind of declaring that I'm like anticipating some kind of a change in X, and I would really like to know over what total length that change in X is going to be enacted. And it turns out that if we start from a static state, that's going to be no compression or stretch, in this case compression. And then if we do the compression, 5 inches. So the spring that normally looked like this is now going to be 5 inches less in height. And that is the amount of work that we're trying to compute over that particular activity. And so now we've got, like I said, the force and the distance built in. We can very easily integrate 10x, that is going to be 5x squared, and we can plug our boundaries of 5 and 0 in. And so just completing the fundamental theorem of calculus should get us 5 times 5 squared, 5 times 25, which is, if I remember correctly, that is 125. And so that's going to take the role of the amount of work that we're going to do. Now, I would like to get a correct unit involved, and our unit is always going to consist of the linear distance times the force, right? So we'll think of distance times force in that order, and we typically separate those with a dash. Inch pounds, so to speak. Yeah, and you could make some claim that the inch and the pounds are in essentially acting as if they're being multiplied together in this case. Okay, now if I were to move my camera over here and then take a look farther down for part C, we're going to do the same problem, but now I want the work, find the work to compress an extra 5 inches. So you're still finding yourself integrating the typical 10x. It's still the same spring, but an extra 5 inches implies that our lower boundary will start at that 5 that we've already compressed to, and then an additional 5 means we're going to be compressing up to a total of 10 inches of compression. So we're going to move our hands even closer together here to make that spring even shorter. And you'll find out when we actually evaluate this, we should get an answer that's a larger value, right? If we plug 10 in, 5 times 10 squared is 500, I believe. And if we plug 5 in, we've already been there. That's our 125. And of course, the net change there is 375 inch pounds. So as you can see, even though we're going to compress the spring the same length, 5 inches, it's going to take a lot more effort, more work on our part, because as the spring is compressed shorter, it becomes more difficult because the spring is sort of fighting back in that capacity. Hopefully that helps a little bit. We do have several more examples coming up that's going to take you through other kind of gambits of engineering and mechanics and physics so that you can really see how work can be applied in a calculus setting. We'll catch you at the next videos.